Welcome to the Guardian Group podcast series. The Guardian Group, providing extraordinary solutions to today's exceptional problems.
Hello, and wherever you may be, Todd Coleman with the Guardian Group once again with another installment in our series of podcasts. Joining me today again is Rick Murrah, and today we're going to talk about leaning pin and dedicated fixtures. First thing we want to talk about is basically what is a fixture. A fixture is an adapter that is used to translate the PCB down to a test machine. For some of us that have been around a long time, these go by the names of test fixtures. Sometimes they call them test heads, but they are an adapter that go between the printed circuit and the machine, and they come in multiple different flavors. We have what we call universal grid or leaning pin fixtures, and we also have what's called a dedicated fixture. And here to join me today is Rick Murrah to talk a little bit about fixture history. Good afternoon, Rick.
Hi, Todd. Thank you for asking me to join you once again. It's always a pleasure sharing our know-how with the outside world. Fixture history has developed for many years. We've both been in the industry for a long period of time now. I remember back in the days when I first started, we had this little small short chisel pin fixture that we called a 1-inch fixture. And I tell you, Todd, you didn't want to turn them upside down. You know what happens when you turn them upside down?
Well, you lost all the intelligence if you happen to save it, and the pins are all over the floor.
That's correct. So we would have to start all over again because you'd have to pick up the pins and then put the pins back in and then make a program. There was no netlist back then. But the fixture history has developed a lot since then. So now we make fixtures when you turn them upside down, the pins don't fall out. Imagine that. There's some sort of rigid material in there that holds the pin in place, or some sort of crimped on the end of the pin to hold it in place. Even if you look at the grid testers over the years, the grid density has improved. So in the beginning, most machines were on 100 mil spacing. So every 100 mils, there basically was a test point. And that test point could be used for a test program. And then they doubled it by making something called double density, but it's not really truly double density. It's a 70 mil grid. So basically the spacing is 70 mils from pin to pin or point to point. And what's interesting there is we had to make sure that our pins deflected into this machine base. So the pins have different diameters, different sizes, and different heads. So sometimes the fixture had a dome head, and the dome head would go on something, a plated edge or gold fingers, where you didn't want to have any witness marks. So a mark left from the test pin itself. So the fixtures can be all different shapes, all different sizes. A lot of people have standardized the fixtures into a couple different stack ups and a couple different sizes in order to achieve more efficient cost. As we get more into this podcast, hopefully we learn about these, Todd. What do you think?
Well, absolutely. That's part of the whole equation. And thanks for that. Talking about leaning pins, I'll pick that one up. Rick mentioned a little bit, we started with the old 1-inch chisel pin, and we kind of migrated into 2-inch. And that's when we started getting into what's called guided plate or leaning pin. And back in the day, the original testers, they had a grid, an interface, like you said, at 100 mil or 70 mil, and they had cup pins they were spring-loaded cup pins that translated the signal down into the test electronics of the machines. For some of those of you that have been out there a long time, the cup pins in those machines, they were great when the machines were new, but as time went on, they got to be a little bit of a problem because flux and solder mass dust and things like that would go down, and then they'd fall into the cup pins, and you'd start getting isolation between the fixture pin and the grid pin, and you'd have false opens. And to combat that over time, what they did is most of the grids went into a serrated type waffle pattern, which was a lot better for contact between the leaning pin and the machine. But enough about that. So leaning pin, what that means is that we have multiple plates. Back in the first leaning pin days of the 2-inch fixtures, sometimes you had a personality plate, then you had a guide plate, and then you had the base plate or the grid plate. And the middle plate or the guide plate was designed to move the pin from the target of the PCB, which we call the personality plate, down to a grid pin on the grid tester or the fixture tester so that the intelligence can be saved, whether back in the day when it was self-learn and save, or when we got into netless testing where we would pick up the signal where it was designed to be. As densities grew more and surface mount got tighter, the fixture leading pin had to deflect the pins much more distance to get all the pins, what we call solved, into the base plate. So we had to go to a higher fixture, which is into the 3-inch and 3 3/4 inch. And the diameters of the pin came down. As Rick mentioned, we solved the problem of tipping the fixture upside down by using a crimped music wire. And that allowed us to get into tighter densities uh, of the new quad packs and chip carriers and things like that. So now today we have both the upper and lower fixture that's universal with a crimp pin, so you can turn one upside down and mount it to a grid tester or a fixture tester. Where back in the day you had to use a combination of a universal leading pin fixture on the bottom half of the machine. If you only had a universal grid on the bottom and no top, which some of the old machines like the old Trace 948, 900 series machines were, and some of the early Everett Charles had uh, nothing on the top, so you had to translate them, and that's kind of a hybrid of dedicated versus universal type fixture. And speaking of dedicated, I'll let Rick talk about a little bit of what a dedicated fixture is.
But I'll tell you, a dedicated fixture is not my favorite fixture. Any idea why I would say that?
Well, it's the mess of wires and mapping to from lists and so forth.
Exactly. So it's very complex to build a dedicated fixture because it needs to be wired. So the simple process would be you need some sort of socket. You either wire wrap in, so you drill a plate. There's not many plates in a dedicated fixture. You can get away with 2 or 3 plates because you're not going into a universal grid tester. You're going to plug the wires into some sort of connector. Now, the connector usually has anywhere from 128 pins, 256 pins, 512 pins. I think some machines even have like 1024. And I saw one machine once have 4096 pins, but that was a lot of big mess of wires going into that connector. The problem is we also use something called a net list. So everything needs to be, the point on the PCB has to be wired to a specific point on the connector. And the wiring is just done by hand. Basically, you have a map, as Todd mentioned, where you got to follow the map, and this PCB point goes to this point on the connector. And you continue on, that PCB point goes to the next point on the connector, and so on and so on. So you go across the connector and you do the wiring, but it's very time consuming. Sometimes they would put a socket in with a wire wrap, as I mentioned, but sometimes they have a socket with a wire on it, where you just have to attach the end of the wire to the connector. And then once you get everything all wired, I guess the next thing you would do then would be to double check your wiring. So you take a toner meter, basically you plug the one end of the connector into it, and you go through the sequence and you make sure that it makes a tone in the order that you wired the fixture. Now, this process takes time, and once you get that done, then you need to put actually the test pin in. So the test pin can be dome, chisel type, crown type. There's various different types of tops of pins that meet the PCB. So you have to insert those pins into the socket. So overall, it is a very time consuming and very costly So in some cases, you may be a few cents for the whole wire. Sometimes there may be $1 or two for the wire. What I find interesting is we used to never make these for many years now, but as the volume increased of PCB runs, it's more efficient to build a wired fixture, a dedicated fixture, than it is to build a universal because they typically last a little bit longer. One thing that I know in the PCB market is a lot of people have technology for sub 1 mil. I think this will be a future podcast, Todd, but if you can build a trace sub 1 mil, then we need to be able to test it. And I know a lot of OEMs out there are requiring 4-wire Kelvin. Sometimes the spacing on 4-wire Kelvin, you need, instead of one test pin on the test point or on the PCB pad, you need two. So sometimes it's maybe more efficient to make a dedicated fixture than a universal fixture, or a leaning pin in this case. But it's very interesting, Todd. So we can go on and on about dedicated fixtures for hours and hours. But I think we should talk a little bit more about PCB drilling. So drilling the PCB versus fixture drilling. What can you
Right.
tell us about that?
Yep. Thanks for the dedicated talk there. I know that, like you said, with sub mill and all that, especially with a lot of higher speed microwave stuff, they've got wire bond, and that's basically a trace that really has no pad or landing pad. It just goes off into the end, and being able to test those with any type of mechanical means is very difficult. But yep, that's a topic for another day. The other thing that we wanted to talk about PCB drilling versus fixture drilling, and what's all involved there. With PCB drilling, you have a drill machine and you can stack 4 or so panels at one time onto the machine, and you let the program go and it drills them all. Well, with a fixture, especially with leading pin fixtures, you don't have that uh, luxury. Basically, each plate has its own personality, so you can't stack up a bunch of plates and drill them all at the same time. So with a PCB versus a fixture, we have an increase in time. Some of the leading fixtures can have 8 to 16 plates, sometimes even more. And each plate is a individual plate, so that each one takes time. So you have to remember when you're doing fixtures, especially leading pin fixtures, that you have a very exponential increase in time, and also time is cost. So you have labor time, you have the machine time, and obviously there's going to be more material because each plate is different. The other thing is talking about equipment. I mean, a PCB drilling machine is a PCB drilling machine. It can drill PCBs, it can drill fixtures. A lot of them can do a combination of routing and drilling. And in the past, a lot of times when a company wanted to do fixture drilling for their test department, they wouldn't really invest a whole bunch of capital into a drilling machine, because usually they had an older machine that was being phased out because the new 9.8 mil or tighter holes in the PCBs required a lot more precise drilling heads and spindles and such like that. So they upgrade to higher tech machines, and then they hand me down these older machines for drilling fixtures, which back in the day was just fine. Most of the older drilling machines could easily drill the holes for the standard type fixtures. But the caveat is, as the complexity of the new today printed circuits has increased, the necessity for the fixture technology to get close and match is also causing problems with the older drilling equipment. So we have to remember that we need to be able to drill basically the same holes, if not even sometimes even tighter than the PCB drilling machine. So we have to basically, in the new arena, uh, probably spreadsheet out some ROIs and possible capital expenditures that we can't necessarily use the hand-me-down stuff for equipment drilling fixtures, because they're just about as high tech, if not sometimes higher, than the PCB you're drilling.
I think if you look in some of our operations, Todd, you will see that we actually have some drilling machines that are specially designed just to drill fixtures. If we're talking about mechanically drilling a hole to accept a 50 micron or 40 micron pin, um, the problem with some of the single spindle machines because, as you mentioned, we can't. If I have a fixture, some fixtures are 24 plates, so 24 plates stacked up on top of each other. That's 24 cycles of the machine. Um, they're not. It's not. It's not. The table doesn't move itself. The spindle moves to keep some of the drag away. So it actually is a specially designed machine. From some manufacturers have them where it's just dedicated to drill fixtures. Now I think the industry has adopted the same sort of thing for PCB boards, but in the beginning it was a specially designed drilling machine just for to drill fixtures.
Right. So we can see from this that, PCB drilling and fixture drilling, two different things. We could kind of combine equipment to do that in the past, but today, like Rick just mentioned, some of this hybrid technology requires, a whole new animal for doing fixtures and test side of the world versus PCB. When we talk about all these pins, Rick, we were talking about leaning pins and dedicated pins and 1, 2, 3 inch. We've got horsehair, music wire, and all these interlocking type things. I mean, how many different kinds of pins are out there?
Oh, that's an excellent question. I couldn't even put a number to that because you have pins with different plating. One of the problems is you assemble the fixture, sure, but what happens if when you go to disassemble the fixture and you get all these pins with diameters that are close together, maybe half mil or 20 microns apart from pin A to pin B? It's impossible to separate them. Yeah, sure, they make some specialized pins sorters that are manually done or mechanically done, but the pins can have different heads, different shaft sizes, different platings, different raw material. So it's very difficult to sort them, and it's very costly to stock them. So a lot of people have standardized on a few different size pins and etc. When you get into dedicated pins and musical wire pins and etc., you have inventories that you may use all the time. You have inventories that you never use. And you have special cases where you get special crown dome type pins made up for a particular part because they have some criteria on the fabrication drawing that requires no marks or maybe marks in a certain area. So you're specially designing a test pin just to go in there. Now the technology has changed, and depending on your pin manufacturer is a very crucial part. You need to have a good qualified manufacturer or partner with a good qualified manufacturer of test pins to ensure the quality. Because remember, this test pin is going to transfer electrical current from the tester, whether it's a universal grid or a connector wire dedicated from the machine to the PCB. So it's going to touch the PCB. So it's got to be well quality controlled to ensure that we're getting the best product back to the end user as possible. But Todd, there's many different shapes, sizes, and lengths. As we mentioned in the beginning, 1 inch, 2 inch, 3 inch, 2.5 inch, 3 3/4. And then in some universal machines, we even go with longer pins. So longer than three, we go up to 4 inches in some cases, depending on how far the leaning pin fixture leans out. Yeah, I remember in the beginning when we mostly had double density machines, we were leaning 1.6 inches, which is a huge number. But when we lean that far out, the pin has to get longer. So you're making a dedicated special pin in that fixture. But a very good question.
That makes me think of another thing when you're talking about leading pins and the longevity of the pin. I've toured many PCB manufacturers over the years, and you get into the test department, and some of the the older text fixture type things, they recycle and dump the pins, and then they use them again and again. And when you get into these really tight diameter small pins, I mean, what's the reusability of this type of product? Is it something you should think you can recycle and use, or is it something that you need to be thinking of an insurance type thing to make sure you use good quality product?
Yeah, for sure. The smaller the diameter is, Todd, it's a single use apparatus for sure. This some pins, yeah, you can use. One of the other problems in the past has always been storage. Where do you store your fixtures? Some people store them beside their plating lines, right? So what? It's very chemical,
That's corrosive.
a very yeah, very corrosive process. So you know the pins come out, even the nickel peels off of them in some cases, and those are not usable again. Or the fixture plate material moves because the XY stability of the plate material is very important as well. All depends on what kind of fixture style you're making and how well it's designed, but you need to make sure that everything stays together and stays within tolerance. But yes, Todd, there's some single
Exactly.
use, and sometimes you can use pins over and over many times. And I've seen people chemically clean test pins as well when they were corroded.
Exactly. Well, folks, I mean, we've given you in a nutshell kind of the leading and dedicated fixtures. And, Rick, where do you think we're going now in the future with the fixture tester and the dedicated? I know, and universal, because I know, everybody has got a phone these days and they make these things millions at a time. Where is the fixture going to, I did an article recently, is the universal fixture gone away by the term, by the way, the dodo? Where are we going with fixtures, do you think?
Because of the volume, I don't think we can get rid of fixtures with the technology that's out there right now. We still are going to need fixtures. Just when you are in high volumes and you're making 40 million iPhones, for example, over a course of a year, of course, spread across many manufacturers, but you still you can't test all those boards on a flying probe at this time. You still have to have something else to test them. And the most economical in this case would be a fixture. You pay a high price for a fixture and you use it a few million times. And that's the best ROI on those type of fixtures. I don't foresee it going away right now. As I mentioned before, more of the market is moving into 4-wire Kelvin testing where you have to put double the test points on the pads in order to achieve the same sort of technology. I'm sure there's some little tricks that the trades have to use a single pin instead of multiple pins, but the correct way to do that is with 2 pins. So 2 pins, and it's the only way to do it.
Right, right. I mean, I know what with the fixtures and you're over millions of boards. I mean, at the end of the day, you spend a little bit more on the fixture, like you said, but your per unit cost associated with testing on a dedicated fixture like that becomes extremely small when your volume's that high, so keep that in mind when you're talking fixtures versus flying probe, if you have the option anyway. Well, with that, I like to thank Rick for joining us again today. Rick, it's always a pleasure having you aboard.
Yes, thank you, Todd. It's always a pleasure learning and discussing our know-how with and sharing the information that we know with everyone out there.
Exactly. And I hope you got anybody that were joining us today. I hope you got something out of this podcast. We try to make it as informative as possible. If you have any questions for Rick and myself, drop us a line at info@guardian.com. That's info@gardien.com. We look forward to seeing you again on another podcast in the future. And we thank you for joining us and have a great day.